Okay, we are live this evening, but we don't have anybody in the live studio audience. But I'm going to get started with session 9 tonight, HF antennas. And you might see a test pattern up there right now. I'm going to put up some antennas here. One thing you don't want is a bunch of ice on your antennas, but this is what can happen to your antennas. I'm just going to kind of preview a few antenna installations here real quick and let everyone see what's out there. You can be as ridiculous as you want, like for instance, this guy here, or even well, there's another one in there, but there's a nice little installation of antennas. Alf at the radio. Hey, everybody knows Alf, right? A little cartoon. The two things that really drew me to amateur radio were the expense and the inconvenience. All right. Let's see what else we got here. Just a quick reminder, get your license pretty quick. The 22nd and 23rd, the fourth full weekend in June is field day. So if you're affiliated with a club and they don't do field day, try to get them interested. If you're not affiliated with the club, find one that is doing field day and partake in the activities as well. Let's see, what else do I have here? Here's another type of installation for antennas. That's quite the arrangement there. You can be as expensive or as inexpensive as your heart's desire. Well, let me tell you, this is probably one of those contest stations, pretty much like K3LR has here in Pennsylvania, Tim Duffy. And he has an arrangement pretty much like this as well. He has quite a few antennas, and that's that's no small feat. It's no small expense. But you can literally work the world on 100 watts and a wire. So you really don't have to get into a lot of expense insofar as antennas are concerned. Um, but you can have just as much fun. You don't even have to have an amplifier. I mean, those are things that if you want later on, you can kind of get into and add to your station or whatever. You can have just a very modest station for the most part, and that's all I started with. My first DX contact outside the U.S. was a ham named Roger down in New Zealand and was on 15 meters CW. So that was quite exciting for me as a novice operator to get in there and do that. I'm going to get the slideshow going here, and again, the topic tonight is HF antennas. It is rather lengthy. There's about 112 slides that we need to go through. So this is the only topic that we are going to cover this evening is HF antennas. And uh, there's a whole variety of HF antennas out there, both for base operation and for mobile operation. Some are, mount to a bumper or the side of the car, kind of lip mount, whatever. If you put a mobile roof mount, mag mounts, um, there's a whole variety out there, and there's a whole bunch of solutions that are available for just about every make of vehicle that's out there on the market today. So you really don't have to be real concerned. And honestly, if you operate HF from mobile, don't think that you're going to not be able to make contacts across the big pond, as we call it, the Atlantic Ocean, and getting into other countries, because certainly that is not the case at all. Yeah, mobile antennas are a little bit less efficient than, say, your big towers with beams and everything outside your house, as you see there in the lower left-hand corner on the screen. But seriously, 20 meters is a very active band, particularly during the day. And I've sat in my truck and I have talked to other countries on the other side of the Atlantic Ocean, Italy, Spain, England, Germany, and stuff like that, right from my mobile. So, and that's barefoot with just the antenna on my car. So you can have HF fun just about anywhere. Traveling across Canada, you won't find many repeaters if you're one of the VHF, UHF users in your car. Um, and you're going into areas that you have big, long expanses of space where you know there's not going to be repeaters, or you suspect that there may not be repeaters. Operating HF in the mobile can help while away some time, and I've done that traveling through Quebec and into New Brunswick and around through into Nova Scotia. And believe me, there is a lot of countryside as you travel through those areas, and you won't find many repeaters or many conversations going on VHF or UHF. But I was able to talk with hams in different areas across the nation, US, particularly on 15 and 20 meters. So you, it's one of those things that I like to do, and you might want to do it too if you travel a lot. So consider getting HF in your car. Let's get right into this. We're going to be right on there. HF antenna. We only have two topics after this. We're going to be covering coaxial cable and RF and electrical safety. And we'll see. I don't know if I can do both of those um, Thursday or not. I might just cover coax cable Thursday, and then Monday do the RF and electrical safety, and then Tuesday we'll might have a wrap up or something if somebody wants to get together for that online live. Drop me an email, Wayne at n3lms.net, and give me your thoughts, any questions that you might have, and we can connect up. I'll help you the best I can, and we'll get this show on the road now. All right, we're talking about the length, and if you remember the formula and everything for calculating antenna length, particularly from your tech class license, there was some um, coverage there for antennas as well, and of course, you were given some formulas in the tech class um, that are very useful as far as determining the length of an antenna for a particular frequency or band of frequencies. So to calculate the length in feet of a half wave, this is a half wave dipole antenna, you need to divide 468 by the antenna's operating frequency in megahertz. So an easy way to remember that is 2468. Who do we appreciate? Okay, nice little ditty there that can help you remember that. Just remember to throw off the two. But 468 is a number that you really want to lock away, much like the 300 number for um, determining wavelength versus frequency. 468 is going to help you determine the length of the antenna, a half wave antenna. Now, again, 234 is a quarter wave antenna. So just kind of remember that as well. So the calculation is very easy with your calculator if you bring it to the exam. One thing about calculators, when you bring them to the exam, uh, if they have a memory, if they're a memory type calculator, the um, the VEs are going to have to check your calculator and make sure you don't have certain things stored into the memories and that the memories are cleared out. Because anything you do on the calculator, you have to enter in manually and not do any recalls or anything of that sort. Any rate, you divide 468 by the frequency in megahertz. In this instance, they're using 14.250 in the 20-meter band to get 32.842 feet, which is rounded to 32 feet. And that's what you're going to answer on that particular question is 32 feet. These are approximations. It's not necessarily exact numbers that we're looking for, but they're approximations. And one of the things that you want to do is choose a part of a band that you want to operate in. And so in other words, if you want the whole 20-meter band, you want to get right in the middle of it. So the 20-meter band goes from 14.0 megahertz to 14.350 megahertz. So if you want to operate the whole band, which includes CW and digital and voice, you want to get that middle frequency, and that's where you're going to um, cut your antenna length for that band in particular. If you just want to operate in the voice band, well, you go to the middle of the voice band or the part that you're going to be legally able to operate in as far as voice, and you're not going to do CW. Just go right into the middle frequency of that portion of the band that's assigned to the general class licensee, and that's where you would make your calculation and cut your antenna accordingly. Now, one thing to kind of keep in mind about antennas is it's not going to be necessarily uh, exactly a perfect SWR. There is going to be some trimming involved. So when you calculate these, let's say for instance, you're going to operate on 14250 like it shows here in this slide, and you want your um, antenna to be 32.842 feet. Uh, Make it 33 feet or even a little bit longer than 33 feet. And using an SWR meter or even an antenna analyzer, if you have access to one, you can actually trim the ends, make sure you trim both ends evenly to get the proper impedance match that you want and the proper SWR for that antenna and for the frequency so that you can at least be assured that you're going to be operating as efficiently as possible. Just kind of remember that. Um, that if you cut it too short and it doesn't work, man, you're going to be you're just going to have to rebuild the antenna. One thing to note too that a horizontal antenna has a higher impedance at the feed point where you're going to put the feed line, and if you bring those ends down to what we call an inverted V, as you bring those legs down on the inverted V, the impedance of the uh, feed point is going to come down and actually come closer to the 50 ohm impedance of the ideal impedance that you're looking for right at the feed point. So just kind of keep that in mind. Inverted V's versus a flat top straight dipole. Let's move right along here with the next one. Here we have, we're doing another calculation, and this involves the 80 meter band. So doing the math is 468 divided by 3.55 megahertz gives you a total half wave length of 131.8 feet. The answer is rounded to 131 feet. One thing to note that this is the overall length. A half wave antenna is we're talking about the overall length. Your feed point is going to be in the middle. So actually, you're going to have two quarter wave lengths on either side of the feed point. So dividing 131 in half, that's where you're going to put your feed point. So you're going to have equal lengths on either side. Probably not a bad idea. Again, like I say, if it says 131 feet, make it 132 feet or 132 and a half feet. And you can trim it accordingly to make sure that you're getting the right SWR and as efficient operation as you possibly can. So, any rate, the half wave dipole antenna does offer a no compromise when transmitting and receiving long range signals. A half wave dipole usually will outperform a multi-band medium length vertical and excel above your fancy 800 mobile big coil whip. Dipoles are really simple to construct, and you can pull up the center section with a rope to configure it as an inverted V. And the only thing that beats a dipole is a big 3-element beam or a quad on a tower. When you put up a dipole antenna, it's always a good idea as well to try to get it at least a quarter wave above ground. A quarter wave above ground will give you some good ground propagation, and if you get it closer than that, you're really going to get a little bit more bounce up into the atmosphere and closer in communications more than you would a DX communication. But propagation is a funny thing, and sometimes we just got to take our chances. The well constructed and properly elevated half wave dipole that is horizontally polarized will generally outperform a ground-mounted vertical antenna. I've got 2 vertical antennas, and I'll tell you, I love both of them. Um, but at any rate, this is because the ground-mounted vertical antenna usually encounters some ground reflection losses from everything close to its base. I have a Hustler 5-band trap vertical or a 5 BTV, and it covers 10 through 80 meters. Right now, it's not functioning, but it needs radials, and it is mounted right just inches off the ground, and it needs a radial system to properly operate and to properly get a good impedance match on the antenna to the transmitter. The other one I have is a Gap Titan DX. It is mounted a little bit higher. It doesn't rely on ground radials, and it is mounted a little bit higher off the ground. It does have a counterpoise, and it covers pretty much all the bands. I can even get 6 meters out of it, but predominantly it's designed for 10, 12, 15, 20. It has 30 meters in there as well, and 40 and 80 meters. So it is a good performing antenna as far as verticals are concerned. But again, that dipole antenna is a really good way to get started out because verticals, most of your DX communications is on the horizontal versus the vertical ground plane. A simple dipole antenna placed between 1/8 and a quarter wavelength above the ground will give you some powerful daytime skywave communications on the 40-meter band. So, but to reach out further, you need to elevate it. This is what I was telling you. You want to try to get it up about quarter wave or better, and that'll give you some good ground wave communications versus the skywave communications. So there it is. You can, if you have a high tree or whatever in your backyard, throw that antenna up there. That puppy will work just fine. The half wave dipole is an outstanding antenna system that will cost you very little to build. This antenna elevated to roof level will generally outperform expensive high frequency mobile whips or expensive trap vertical antennas and pricey automatic tuner fed long wires. But get the half wave dipole up high, as high as you possibly can. And if it's less than a quarter wavelength above ground, the feed point impedance will dramatically decrease and your radiation pattern goes wacko, not to mention that you now have a source to load impedance mismatch that will affect your output power. If you try to offset the feed point of a half wave dipole from the center towards the ends, the feed point impedance will rise well above 50 ohms, and your rig's automatic antenna tuner may have a hard time correcting to an SWR of 1 to 1. I have an off, excuse me, I have an off-center fed antenna designed for 160 meters, and what I mean by off-center fed is that one leg is longer than the other leg, and there's ways you can there's formulas for that to make an off-center fed. You can look online, you can get some really um, good information off the web. If you go to AC6V's website, he is that particular site is let me see if I can pull it up here. AC's oops 6v dot com. I think it's com.org. Yep, there it is. So let me get that over here real quick, kind of show you this website real quick. AC6V has put together this compendium of information of everything relating to ham radio. And there's books, there's things to FM. Here's your master index here that shows antennas, homebrew, software. I mean, it's got all kinds of stuff there. But you can go into these links, and you can get all kinds of information here about antennas, basic design and theory, dimensions calculator, all kinds of little utilities and things of that sort. So remember that AC6V is the website, and it's .com to kind of keep as a handy URL link on your web browser. So there you go. I'll bring this back over here, get back into this. Uh, any rate, you can find designs there for all types of antennas. Let's see. If you try to let's see, if you try to offset the feed point, uh, this is in my way. If you try to offset the feed point of a half wave dipole from the center towards the ends, feed point impedance will rise well above 50 ohms, and your rig's automatic tuner may have a hard time correcting to an SWR. Typically, it can be around 400 to 600 ohms. The Buckmaster antenna is a very broadband type antenna that has been designed, and it's an off-center fed type antenna that gives you fairly good SWR on just about all of the ham bands. And if you want more information on that, um, let me see if I can pull that up again, maybe show that to you as well. Um, let's see, where is it? The guy who does the ham call website does that as well. Let me see if I can bring this over here and kind of show you what the Buckmaster looks like. That's the Buckmaster. You got a 7 band, you got a 4 band, an 8 band, but this is predominantly what it is. And one side is shorter than the other, and this they got this ruler here to give you an idea of the size. But it's good to have a nice bit of property to hang this up. These balins here will help match your 50 ohm feed line to the proper impedance of the feed point of the antenna itself. So look that up. Go to hamcall.net and you can get some information there on that particular dipole antenna or try to build one yourself. Just some information there. Moving right along, the dipole gives you a figure 8 pattern at right angles to the antenna wire, so reception and transmission are minimal off the ends of the wire. Again, that gives you a figure 8 pattern at right angles. We're going to see that here in just a moment. Okay. There's kind of like what your pattern is going to look like. Never mount a dipole antenna less than a half wavelength above the ground for long range DX, if at all possible. I tell you this, I my 160-meter antenna is not a half wave or not even a quarter wave above ground. I can actually reach up and reach the ends on both ends of it. However, the feed point is about 24, 25 feet above the ground, which is again below the quarter wave recommended height that it should be. But I get some really good skywave, what's called near vertical reflection, that gives me good close in signals and communication capability. As a matter of fact, I can reach up into New York and New Jersey and even up into New Hampshire, Vermont, and those areas as well, down into like West Virginia, Virginia, and the Carolinas possibly. And I'm here in Pennsylvania, and I'm on a mountaintop, so I have a fairly good arrangement here. Um, just to kind of let you know. But the higher you get it, the better you have the possibility of getting some good DX out there on your antenna. All right, let's imagine you go out on a camping trip into a valley 200 miles away from your buddy's house. So, with a normal dipole up about a half wavelength, your 40-meter signal literally skips over his location. But a neat way to pull in your first skywave hop is to lower your dipole so it is just high enough that no one can touch it. So you'll find that your first skywave hop now arrives at your friend's house loud and clear. Dramatically lowering an antenna will develop a higher elevation angle of radiation, causing your skip distance to pull in, which establishes shorter than normal skywave communications. And what that signal's doing literally is it's going up bouncing off the ionosphere instead of going out further. So you get a little bit different angle of transmission that reflects back a little bit closer to your location. And that's what happens with my 160-meter dipole antenna. The dipole antenna is fun to play with when strung between two trees using two pulleys. And so you string it up high and your angle of radiation lowers, yielding a longer distance for your signal. However, if you want to talk to your granddad who's about 300 miles away, try lowering the dipole real close to the ground and notice that the distant skywave skip will fade out and good old granddad's signal just a few hundred miles away now comes in strong. And so this is because your skywave is nearly vertical. So it's going up at a nice sharp angle, bouncing off the ionosphere and bouncing back not that far away from your location. So again, raising that antenna up high gets you good DX performance and long distance performance. Lowering it down closer to the ground gives you a little bit of that vertical, sharp angle, near uh, communication type effect. To get your dipole to operate like an NVIS antenna, start near ground level and work up from 1/10 to a quarter wave. And listen with each change in height as closer stations get dramatically stronger. Something I haven't done with the 160 because it wouldn't do any good for me anyway. I can't get it up any higher than where it is now. So I don't bother. I'm perfectly satisfied with it. I also use a tuner on the 160-meter antenna for 80 and 40-meter communication. It works really great for both of those. And I can't really use it because of the length of it on any frequencies any higher than that, like, 20 meters and 15 and 10 and things like that. But I do have a dipole. Well, actually, I have an inverted V. It's called a fan inverted V. And it's got uh, three dipoles built into a single feed point that um, are cut for 20 meters, 12 meters, and 15 meters. Um, I use the vertical for 10 meters, however, but I can also use that inverted V, that fan inverted V for 10 meters if I use a tuner, and it works quite well. So just, different options are available to you. And the reason I don't put up a beam antenna here on the mountaintop, um, antennas tend to get destroyed with the winters around here. We get some very blustery winds. When I put up the gap antenna, which is a very, very tall vertical antenna, it really tended to whip around quite a bit um, in the um, in the wind, and actually bent this heavy m- metal pole that I had it mounted to. Actually, put a slight curve into that pole by one wind occurrence that we had, and I was really concerned that the antenna was just going to be scrapped by the next morning. So I ordered the guy wire kit for it, and now I'm not too concerned about it. But I don't put beams up here because of the wind and the ice that accumulates. I've had antennas destroyed, and these were just simple vertical antennas for VHF and UHF. And I've had to go from the aluminum or metal type antennas to fiberglass antennas up here. So I'm perfectly content with running wire antennas and being on top of the mountain. I really don't need a beam antenna because I can talk just about literally anywhere in the world with what I have here. So you don't have to go to a whole lot of expense or be too concerned about what kind of antenna you have. The military and emergency communicators will use NVIS dipoles mounted just a few feet above the ground. This configuration causes the signals to take off in an almost vertical direction or a very sharp angle, and it'll go into the ionosphere, and the signal comes back down much closer than a regular dipole up a half wavelength. And it's a great way to get some short skip distance during the day. And it one of the things to really hone. Yeah, I mean, you can buy a good radio, you can have the best radio on the market and everything, but if you don't have a good antenna system, and if you don't have a good understanding about how the antennas work, it's going to suck for you. So you really, really need to think about your antennas and what you want to do and how you want to do them. And don't be afraid to experiment. I had one guy who was really having a problem with um, his getting signals, DX signals, and just kind of listening to his configuration a little bit. Um, it seemed like he had a situation where he had a piece of equipment in line that was kind of redundant. So I told him, I said, you need to take that piece of equipment out and just have your meter there. And since he had a built-in antenna tuner, he didn't need one, even though the antenna tuner was in bypass, the external one that is. Um, it still affected his signal going up the antenna. It really sucked. And once he did that, he was able to work some DX across the Atlantic Ocean. And so he was much happier there. But to experiment a little bit with antennas is probably one of the things that many hams are into these days. I like working with antennas, and it can be a challenge basically. But just to understand how they operate, the closer to the ground, the more vertical your transmission is going to be, and the closer you're going to be able to communicate that way. The feed point impedance increases from 25 ohms to 50 ohms when you bend the radials downward. Remember, most general class transceivers are designed for 50 ohm impedance match. And they're talking about vertical antennas here, by the way. The feed point impedance increases from 25 ohms to 50 ohms when you bend the radials downward. If you have a vertical antenna, it's going to have radials around it. If you look real close, and I think this picture's in your book, if you look real close, there's a vertical antenna up here at the top of this pole. And if those were bent down just a little bit, it would come closer to 50 ohms. 25 ohms still isn't really bad, but I know that if you homebrew vertical antennas, it's important if you want that good match to actually slightly bend those radials down just a tad bit to give you a more even 50 ohm impedance match. They are slightly sloping down, I think, is what this is. Not much, but some. You don't want to do it at 45 degrees, just very slightly, and that'll help. All right. So let's say you want to operate 10 meters mobile. When you operate mobile, the metal frame of the vehicle makes up about a quarter wavelength of your antenna system. And the other quarter wave is the vertical radiating antenna. If you think 10 meters, of course, is close to the 11 meter or the CB band, what's called the CB band now. And if you see those mag mount antennas on the roof or on the trunk of the cars and everything, um, you know that the antenna itself is what you have. There's a coil probably in the base of that thing, and the car acts as a ground plane and makes up the other portion of the antenna. You have to always, in most situations, have to have a counterpoise of some sort. So the car acts as a counterpoise to the vertical radiator. You got to think of your vertical whip as one side of a dipole and the vehicle chassis as the other. So to calculate the length and feet of a quarter wavelength vertical antenna, first find the length of a half wavelength in feet, then take half of that. To find half a wavelength, divide 468 by the antenna's operating frequency in megahertz, or you can use 234. So divide it into 234 instead of 468. It's pretty easy. But at any rate, what you do here is that you divide 468 by the frequency in megahertz. Let's say it's 28.5, and you get 16.42 feet. Then 16.42 divided in half is about 8.2 feet, rounded to 8 feet. And that's why when you also see back in the CB days, A lot of people had those whip antennas mounted to their bumpers or off to the side on a ball mount on the side of the vehicle. And they were about 8 feet long, definitely. And so that was a quarter wavelength for CB. So there you go. All right. Ground radial wires are important for the ground mounted vertical antenna to establish its own counterpoise. To hear any real difference when you already have a few radials laid out per band, you must double the number of radials. If you have two per band, try four. If you have four, try eight. If you need more ground plane than eight radials per band, try mounting your antenna on the aluminum shed in the backyard and use the roof of the shed as a substitute for the radials. Bottom line is the more ground radials you have on a ground plane antenna, the lower the takeoff angle of radiation, which means more DX. Get out the shovel and start digging to install more ground radials. What I did for my 5 band trap vertical was I laid out three radials and I cut the radials themselves, um, the length for the band that I'm operating on. And that seemed to work quite well for me. That's one thing about the Hustler 5 band trap vertical or 4 band trap vertical, depends on which one you get, is that not only do you have the ability to tune the antenna by sliding it, the particular portions, the LC circuits networks on the vertical for the band that you're operating on, but also the length of the radials will also affect how efficient and how the impedance is for each band that you're operating on. And so you can easily adjust the impedance value or the SWR by cutting your radials to length as well. Now, they say you don't have to, but that's what I did. So what I did was I had three 80-meter radials, I had three 40-meter radials, and then I put in four each for 20, 15, and 10. And that was a pretty good radial system. And unfortunately, for some reason or another, some of them worked up out of the ground, and mowers and radials don't really go together. So I've got to rework that and get that back together. Any rate, that's why it's important to get them underground, and hopefully they won't work themselves out. Another good way to do that is to take a chainsaw and with a bad blade on it, and just run that chainsaw out through the ground and do yourself a little ditch that way, and you can just stuff the wire down in that little ditch and then cover it over, and that works quite well too, rather than getting out the shovel. It also is a little bit faster and more efficient. Just make sure you don't have anything else underground that your chainsaw might cut into, and of course that chain's going to be ruined by the time you're done, because you're going to hit rocks and all kinds of stuff underground, but it'll be good enough for cutting into the dirt, and that's why you should just use a rather dull chain if you're gonna use a chainsaw that's already you're gonna throw away anyway, and that way you can plant your radials underground more efficiently. An antenna with appreciable gain in one direction is called a beam antenna and always has an equivalent null or nulls in some other direction. All beam antennas, such as Yagis, function by redistributing the power that's supplied. As in every other situation we've encountered, NFL no free lunch applies. An antenna can only increase signal strength in one direction at the expense of a decrease somewhere else, which is not necessarily a bad thing. Deep nulls off the back or sides of a directional antenna can greatly minimize interference. I have a 2 meter antenna up here. It's a 13 element antenna. I have it pointed away from Pittsburgh because Altoona here has a 6-1 repeater, and so does Pittsburgh. So being up here with a vertical antenna, I can bring up three 6-1 repeaters. And so I put this beam up here. Of course, I use the beam for other things too. I like to work a little bit of 2 meter single sideband down on 144.2. And that's kind of fun too. You might want to try that. You can get some good distance out of 2 meters sideband, believe it or not. But a beam works well for it anyway. But you have a null in a direction which is called or referred to as the backside of the antenna. So a directional antenna can greatly minimize interference in a particular direction. So here you have picture a beam antenna, and on a three-element beam, the director is the shorter than the driven element, and the reflector is longer than the driven element. And what we see in this picture here is we have the driven element in the middle, and we have the director in the front, and we have the reflector in the back. So your signal is going to go out this way in the direction of that arrow there. And this is kind of a little directional pattern reference as far as what your radiation pattern should look like coming off of that antenna. Now, sometimes if you decide to do some home brewing beam antennas, there's different ways you can do this. This would be a typical three element beam antenna, but there's nothing that says you can't put the driven element up front as long as it's the right size. So this one here would be pushed up front. You would have this reflector pushed to the middle and another reflector slightly longer on the back, and you could do it that way. There's no particular reason that I'm aware of to do it that way, but some antennas are that way, and that's perfectly okay. But you can play around and experiment with beam antennas if you so desire. But since the Yagi antenna is a series of dipoles affixed to a boom in the same plane, the driven element is about a half wavelength long. The reflector is a little shorter, and the director is a little bit. The reflector is a little longer, and the director is a little bit shorter. Just remember that. And that's what pretty much gives it its directional capability. Now you'll see sometimes the driven elements, actually the beam antennas, if it's a tri-band, you'll have loading coils on there to simulate a half wavelength. They're not physically a half wavelength, but electrically they're a half wavelength. Yeah. Okay, you can always figure out which way to point a three-element Yagi by seeing which elements on the boom are the shortest. The reflector is normally the longest parasitic element. The directors are usually 5% shorter than the driven element. The shortest elements of the Yagi always point in the general direction of the distant station. So most worldwide Yagis are horizontally polarized. On a Yagi antenna, boom length determines the amount of gain. So the number of elements and the diameter of the elements influence the directivity and bandwidth of the antenna. But it's the boom length that determines the amount of gain on your antenna. The main lobe is the main radiating direction of the signal. Use a field strength meter to determine the main lobe of most directional antennas. Incidentally, many beam antennas, such as broadside arrays, curtain arrays, unterminated rhombics, V beams, and even quad loops are bidirectional with two equal gain lobes 180 degrees apart. In other words, your null is going to be off on the sides and not off the back or the front. So your nulls on the side are where you will transmit no signal, but a bidirectional antenna will transmit both front and back, or if you want to use that designation. The Aggie antenna gives you an excellent front to back ratio, and this means that the majority of the power is radiated out of the front of the antenna with little signal wasted to the back or sides. Most of your power is going out in the direction of that antenna, and it's not radiating out in all different directions. It's going in one direction. Anytime you begin lengthening the boom, adding or subtracting elements along the boom, or spacing the elements differently on a Yagi antenna, you will affect gain, front to back ratios, and SWR bandwidth. So all the choices are correct on this particular question. The greater diameter of the elements, the greater the bandwidth. So if you have like fat elements, you get a better bandwidth out of it. If you have skinny elements, your bandwidth is going to be much more narrow. So the greater the diameter, the greater the bandwidth, and this is why a wire beam antenna does not offer as much bandwidth as one constructed of large aluminum tubes. Yeah, you can construct a beam antenna from wires if you want, and that's perfectly okay. But your bandwidth, the usable amount of bandwidth on the frequency band, is going to be very limited. So if you use aluminum tubing, that's great. Uh, use half inch, 3/4 inch, 1 inch, 1 1/4 inch, even better. And if you want to experiment with beam antennas, and you'll increase your bandwidth, the larger diameter uh, tube you use. If you decide to construct your own 3-element beam, chances are you will need to develop a feed point connection. And that will take relatively low feed point impedance up to 50 ohms to match the impedance of your coax. There's a gamma match that most of these antennas have, and it's a line matching system that lets you tap the driven element at a preferred 50 ohm feed point. The gamma match may look like a short circuit to an ohm meter, but to your radio signal, it will look like a perfect match. And it's just a little tiny stub that kind of hangs off the driven element, and you adjust that connection between the stub and the driven element to obtain the proper 50 ohm match. And you can look at that using um, uh, an antenna analyzer, much like the MFJ 259B, which I have. Your HF Yagi antenna may achieve a more predictable radiation pattern by insulating all elements from the boom. Big improvements in those element insulators keep them from cracking when a giant crow lands on one of them. So, some high frequency antennas couple the elements directly to the boom through the stainless steel hardware and alignment brackets. This simplifies the matching network to the popular gamma match. With the gamma match in place, you can hook up a Yagi antenna directly to a 50 ohm coax feed. And while the pattern may not be quite as predictable, the gamma match metal to boom high frequency antenna is a solid performer. And here we have vertically stacking horizontal Yagis, which helps concentrate the main lobe in elevation for added signal strength to the desired station. And we see here a pair. This is a pair. These two are what we want to call co-phased or matched uh, to um, to maximize the signal. So there's a pair of long beam antennas on Gordo's tower that adds 3 dB over a single antenna of the same type. So, in other words, this configuration, what he has here, whatever power goes into these antennas, and let's say that each antenna is a 3 dB gain in and of itself, and you have 100 watts feeding into this. 3 dB essentially equates to twice the power that's being fed to it for an effective radiated power of about 200 watts. So if you stack these, he gets an additional 3 dB. So essentially, he's got another 400 watts effective radiated power by using these two antennas together. And he's only feeding it with 100 watts. Well, I don't know exactly what he's feeding it with, but that's just as an example. And that doesn't include the losses. Of course, there's going to be losses along the way, and it may be slightly less than what I said. But just remember, there's always going to be loss in your feed line. There's going to be loss at your connection points. And while most of the time those connection points are minimal, The majority of your loss is going to be in the feed line. You don't need a linear amplifier to boost your effective radiated power output or increase reception. You can stack a pair of Yagis about a half wavelength apart and double your transmit and receive gain. Remember, 2 times the gain is 3 dB. A great way to get started on 40, 20, and 15, and also 10 meters is with a trapped dipole, a trap beam antenna, or even a trap vertical antenna. And that's what my 5 band trap vertical antenna actually is. Um, if you don't know what it looks like, I'm going to bring that up real quick. I'll bring it up. 5 BTV Hustler. Do, 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 do. I don't like that picture. Let me get a better one here. Da, 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 da. Oh, that picture looks okay. Doesn't look like much there. I see that. I know it's a little blurry. That's because the original is a little small, so I'm kind of getting blown up here. This is where it mounts at this point. So this would be my 10-meter section. This would be the 15. This would be the 20. This is 40, and this is 80 right here. This little capacitance hat kind of keeps, that's what it's called for 40 meters, kind of keeps off your, helps with your matching for 40 meters. And you have a little uh, coil up here for 80 meters, and you can adjust that. Your radials would attach down here, and they would go out in all directions, and you can tune these by running them up and down. And these are what's called traps. So this is a 5 band trapped vertical. We got 1, 2, 3, 4, and 5 bands, and they're predominantly LC networks in there. Anyway, the traps allow the antenna to naturally tune to specific ham bands. Gordo operates a 4-element 4-band beam antenna. The traps work great to give him high frequency operation on multiple ham bands with only one antenna. And I've seen antenna farms where they have several single band antennas. Um, in my first days, the early days of my ham radio hobby, down the road, not too far from me, was a guy who had probably about 5 towers put up. And on one of his towers, he had a 40-meter beam antenna. If you can imagine, it's a full size 40-meter antenna. There weren't no traps on that thing, and it was humongous. But if you space is at a premium, using a trapped antenna is the way to go. They can be quite compact. I had what was called a mini quad many years ago, and it was able to do 6, 10, 15, and 20 meters. And it was a very, very compact antenna and a very unique configuration. And I could work the world on that as well. All right. Newer HF radios have internal bandpass filters to minimize harmonics. A harmonic is a multiple of your fundamental frequency that causes problems when you realize you're transmitting on 2 frequencies at once. So if you're transmitting on 7 megahertz, you want to minimize any harmonic on 14 megahertz that would interfere with nearby hams on that frequency. Unfortunately, while multiband antennas have many advantages, they also have the disadvantage of poor harmonic rejection. So it is quite possible that if you're operating on a particular frequency, let's say 40 meters, and you're not going to be right exactly on 7 megahertz. But if you have a second harmonic on there that's operating in the 14 megahertz range, you could be broadcasting on a harmonic frequency that you're not legally allowed to broadcast or transmit on. So remember that multiband antennas have very poor harmonic rejection. Unless you use a remote mounted automatic antenna tuner, the random wire antenna can put a lot of RF feedback in your station. Think about that. Um, Remote mounted automatic antenna tuner. That means remote mounted at the antenna. And you can have the potential of RF feedback in your station. That's a reflected signal back into your transmitter. Most antenna tuners built in today's HF transceivers have a limited tuning and matching range and are incapable of efficiently handling gross mismatches. If you have an antenna that is, um, let's say you've built yourself thrown up a random dipole antenna. You haven't really taken any calculations. You just want to put it up there. You don't know what band it's going to be in. The antenna, if you have a built-in antenna tuner in your rig, doesn't have the capability to match that antenna very efficiently to the frequencies that you want to operate on. It's always best to have an antenna that is at least close to the frequencies that you want to operate on. That's why they give you the formula to calculate the best length for the band you want to operate on. So many hams do like the versatility of using open wire feed lines with an external antenna coupler or tuner that can handle just about any kind of mismatch with negligible loss. If you anticipate using open wire feed line, a good external tuner is a must. Your transmitter will never see what's on the other side of the tuner. It will just see a 50 ohm load that your tuner presents to it, irrespective of how inefficient the signal is going down the feed line to the antenna. The thing is, your transmitter is happy because it sees a match, an impedance match. The decibel is a unit of comparison which is somewhat meaningless unless you have a reference point to compare it with. In the antenna business, we have two common references: the isotropic radiator and the dipole antenna. Now, the isotropic radiator doesn't really exist in real life. It is a theoretical antenna. And but if it did really exist, the gain would be 0 dBi, or decibels reference to an isotropic radiator. Whenever you see dBi, that's referring to an isotropic radiator, which has absolutely no gain, but it equally theoretically radiates equally in all directions, 360 degrees, and is a perfect match to your transmitter. However, let's talk about the dipole antenna, which has a gain of 2.15 dBi, which is 2.15 decibel over the isotropic radiator. And it also has a gain of 0 dBd, which is referring to decibels referred to a dipole. The D is a dipole. I is the isotropic, D is the dipole. So you got to remember that. The dipole is a gain of 2.15 typically over the isotropic radiator. For the purposes of reference, okay, when we're talking about 0 dB gain um, with a dipole, we're only referencing the dipole itself. And you might see antennas that say, okay, this antenna has a gain of 3 dBd, meaning it has a 3 dB gain over a standard dipole antenna. And if you just consider and think that a dipole antenna is 0 dB in and of itself, in other words, what power you put into it is the power that's going to go out of it. A beam antenna with a 3 dB gain over a dipole antenna would be twice whatever you put into it. So just kind of remember that. dBd references the dipole. So it doesn't matter which reference you use as long as you know what that reference actually is. If an antenna is specified by its gain in dBi, that figure will be 2.15 dB, greater than if it's specified in dBd. Um, so you have to be very careful with how a beam or any type of gain antenna is referenced. Is it referencing the gain over an isotropic, or is it referencing a gain over a dipole? Just something to kind of keep in mind. Remember, the decibel is a figure of comparison. So, unless we know what we're comparing, it is a meaningless figure. In antenna work, there are actually two commonly used dB references. One is the isotropic radiator, which we just talked about, and the other is the dipole antenna, which we just talked about. Again, the dipole already has a gain of 2.15 dB over an isotropic radiator, which is about twice the power of a perfect isotropic antenna. So let's say a manufacturer sells you an antenna with a gain of 4 dBd. To know what its gain is in dBi, simply add the 2.15 dB gain that the dipole already has. An antenna with a 4 dBd will have a gain of 6.15 dBi. So note, you will never see an actual isotropic radiator. It is a theoretical reference point that is commonly used in antenna work. And this is why I was saying, for the most part, a dipole antenna in and of itself, referenced by itself, is a zero dB gain antenna with a 2.15 over an isotropic. So be very careful when you read those references of how much gain that antenna that you're potentially buying actually has and what it's referenced to. The cubical quad antenna is a four-sided wire antenna system that incorporates a full wavelength for the band. Isn't that convenient? Its performance is identical to or slightly better than a Yagi. Each side of the cubical quad is a quarter wavelength, so use the following formula to determine the length of wire needed for each side of the driven element of a quad antenna. And whatever it is in feet is equal to 1005 divided by frequency in megahertz divided by 4. So it's very easy to do, and that gives you the length of the wire for each quarter wavelength side. There's a two-element cubical quad antenna constructed of wire and fiberglass spreaders, while a three-element Yagi antenna is constructed of aluminum tubing. The cubical quad is much more fragile and subject to damage from wind, ice, or snow. If you live in the Northeast where severe icing might quickly destroy the two-element cubical quad, or if you're planning to leave this antenna in place for an extended amount of time, it's best to consider a three-element Yagi over the two-element cubical quad. So whatever it is, the gain is about the same, by the way. Remember, reflectors are generally 5% longer than the driven element, and the director elements are 5% shorter than the driven element. You want to catch all the reflection, in other words, bigger reflector, and concentrate it as a point as you point it so it goes farther with a smaller director. So it's usually better to have that driven element, and you can have one or two directors and maybe one or two reflectors. 5% is the key, however. Since the quad antenna is a full wave loop, each side of the element is about a quarter wavelength. The reflector element is always slightly longer than the driven and director elements of the quad antenna. Just remember that. Nothing more to really understand other than that the reflector element is 5% longer than the driven. The director is 5% shorter than the driven. All right, you've built your own cubicle quad for the band of your choice. So if you feed coax cable to the center of the horizontal side, the signal will be horizontally polarized. If you decide to feed the quad in the center of the vertical side, guess what? The signal is going to be vertically polarized. So you just, wherever you plug that in, if you're going to operate vertical, a vertical antenna is vertically polarized, a horizontal antenna is horizontally polarized. Delta loops. Well, it's another version of a full wavelength antenna system. And of course, each leg is one-third wavelength long. That's for each side of the symmetrical delta loop antenna. And a delta loop antenna, let me see if I have one here. Basically, it's a triangle. And you want to try to get that up as high as possible. And typically, if you're running it on 80 or 160 meters, you've got this messenger wire or anchor wire that strings between two locations, and you're going to feed your delta loop, attach it to the top there, and come down at the angle, and you're going to have another one down at the bottom, another element across the bottom in kind of a triangle configuration. So the formula is very similar here. If you're going to produce or build a delta loop antenna, and there's plenty of books on how to build wire antennas. So just as you did for the quad, you divide each side of the driven element in feet is equal to 1005 divided by frequency in megahertz, and then divided by 3. That gives you the length of each side. The delta loop beam antenna looks like a triangle with each side being 1/3 wavelength long when compared to a 4-sided cubical quad antenna, but the gain is still almost identical. The logarithmic periodic antenna is quite the antenna. The length and spacing of the elements increase logarithmically from one end of the boom to the other. These are very big antennas with limited applications for specific ham radio bands. It's always best to go with a multiband dipole or a multiband beam long before you even consider the monster logarithmic periodic antenna. Um, Matter of fact, there's a picture of it in your book. You'll find some military stations. I know the FCC regional, the FAA rather, the FAA Regional Control Center in Leesburg, Virginia, has a big logarithmic antenna outside for their use. But military stations may use this system called a log periodic. The elements get progressively shorter on a very long boom, allowing for a wide bandwidth over many megahertz of radio bands. That's one of your main advantages of the logarithmic or the log periodic antenna, is it has a very wide bandwidth. And so the SWR does remain flat on the HF log periodic antenna from 10 megahertz all the way up to 50 megahertz. And the only problem with a log antenna is the low forward gain achieved with such a monster on the air. Typically, they're built with tower sections as the boom, and it sits on a tower section, as you can see in the picture. They're awesome antennas. They're just not very practical for ham radio use. If you have plenty of real estate, the low and long beverage antenna can achieve some great directionality. This antenna lets you either home in on a specific signal or minimize noise coming off a nearby antenna line. The low and long beverage antenna. Some of the larger high frequency base station rigs have a separate antenna port for an optional receive antenna, and that's perfect for your beverage antenna. You don't really want to transmit on the beverage antenna anyway. It's mostly for receive and for the purposes of bringing in signals a little bit more efficiently without a lot of noise. Any rate, sounds like a soft drink, but the beverage antenna is actually a fabulous shortwave receive antenna. It is excellent at pulling in distant stations with minimal atmospheric noise. However, use it as a receive only antenna because its transmit losses are high when compared to the common dipole. When you think about the beverage antenna, as its name implies, think of it as just sitting back, enjoying a nice cool drink, and listening. So that's why it's really good as a receive antenna. 75 meters is a great nighttime band for talking more than 1,000 miles away. However, to get on 75 meters with a mobile unit, you need a monster antenna system. Getting all the parts of that system mounted and working properly will be your biggest challenge when operating mobile on 75 meters. There are lightweight fiberglass, stainless steel high frequency mobile whips, and they provide some fairly significant performance. However, the resonant bandwidth of these antennas may only be about 20 or 30 kilohertz wide. Kind of keep that in mind, especially on 40 meters and 75 or 80 meters. Resonant bandwidth of the mobile antennas, HF mobile antennas, are very narrow in bandwidth. Oh boy, the egg beater. Let's see, it's a 40-meter high frequency antenna. It's a capacitance hat, which makes any antenna look electrically longer than it physically is. So on 40, 70, and 160 meters, when operating mobile, you really need a good capacitance hat to gain a little bit more radiation capability. So when you're transmitting, the high frequency mobile antenna carries some very high voltage at the tip of the whip. You can actually create a corona ball at the tip of the mobile antenna, and it can actually create some interesting effects at the tip without the corona ball. So to minimize sparks coming off the tip when you transmit, make sure you have a corona ball at the tip of the mobile antenna. Never operate in close proximity to trees, even 100 watts. The signal could arc from the tip of the mobile antenna with or without a coronal ball to a nearby tree branch. Yep, sure could. There in that picture, you see the MFJ 259B antenna analyzer. Um, the invention of this little device is a real improvement for anyone working with antennas, and it allows you to test the SWR of the antenna without risking your expensive HF gear. The analyzer is hooked up only to the antenna and feed line to determine the standing wave ratio measurement. It actually does a lot more than that. It can actually tell you the condition of your, give you an approximate condition of your feed line, as well as impedances and other indicators if you want to get a little bit more high tech in the development and working with antennas. And there's lots you can do with the antenna analyzer, such as ringing out coax cable for opens and shorts and determining the resonant frequency of an antenna, determining the impedance of that unmarked coax cable. If you have unmarked coax cable, it can tell you whether that feed line is 50 ohm or 75 ohm. Could be you've gone to the ham fest, you bought a big, huge box of coax cable, and you get home and you don't know what it is, but you put your antenna analyzer on it. Voila, it's all TV antenna, and it's all feed line, and it's all 75 ohms. Not that you can't use it, you certainly can still use it. Well, at least you know. Any rate, what happened to Gordo was he was doing some SWR analyzer checks of his 3-element beam after a big rainstorm, and for the first 30 seconds, there was a perfect dip right at 14,250. And then all of a sudden, the SWR analyzer showed intermittent spikes in the standing wave ratio, looking like some sort of intermittent connection. There were short spikes and long spikes. Any rate, it was his neighbor across the street, Jim N6JF, operating CW on 20 meters with just enough power to cause his analyzer to dance around with dots and dashes. And as soon as he stopped transmitting, things settled down to normal. The fact is, most SWR analyzers will freeze up and or become erratic when trying to measure an antenna at a repeater site because other strong signals will interfere with the antenna being tested. Just got to remember that. If you're just looking for relative output, a nice little portable field strength meter is a good addition to any ham station. And it just gives you a relative strength in proximity to the antenna when somebody, your helper, is transmitting inside. A well calibrated field strength meter might be used to determine radiation patterns off the brand new ground plane antenna. Um, I'm gonna have to move along here pretty quick because we're almost to the question section, and we're about 20 minutes after 8, and I want to kind of wrap this up. But at any rate, well calibrated field strength meter is used to determine radiation patterns. The real world of radio, the only way to properly measure antenna pattern field strength is out in the middle of a 5 acre field where the ground is absolutely flat. There are no buildings. So the antenna is then rotated with the field strength measurements at a specific fixed spot. and forget about trying to calculate antenna patterns of a vertical antenna in your neighborhood. It just won't work. Oh, here we go. We are at the question pool at this point. So I'm going to get right into it since I have nobody live in the broadcast tonight. I guess everybody has to work, and we'll go right to it. So the approximate length for a half-wave dipole antenna cut for 14.250 megahertz, and if you remember correctly, if you haven't memorized it, divide 14,250 into 468, and you get approximately 32, a little over 32 feet. D is your answer. The approximate length for a half-wave dipole antenna cut for 3.55 megahertz. Again, you divide that figure into 468 and you come out with approximately 131 feet. Which of the following is an advantage of a horizontally polarized as compared to vertically polarized HF antenna? So the advantage of a horizontally polarized antenna compared to the vertical antenna is that you really get lower ground reflection losses. Which of the following antenna types will be most effective for skip communications for 40 meters during the day? You We talked a little bit about this. We were talking about the near vertical type antenna, and the best way to do that is to use a horizontal dipole placed between an eighth and a quarter wavelength above the ground. So how does the feed point impedance of a half-wave dipole antenna change as the antenna is lowered from a quarter wave above the ground? As you lower that antenna from high up down to closer to the ground, the actual feed point impedance will decrease um, a bit. So remember that. How does the feed point impedance of a half-wave dipole change as the feed point location is moved from the center towards the ends? Okay, if you move that feed point from the middle to one of the ends, it steadily increases. What is the radiation pattern of a dipole antenna in free space in the plane of the conductor? The radiation pattern. And that was pretty easy. If you remember, it's actually in a kind of a figure eight at right angles to the antenna. How does antenna height affect the horizontal or azimuthal radiation pattern of a horizontal dipole HF antenna? The height, we're talking about the height of the horizontal antenna. Remember, if it's less than a half wavelength high, the pattern is almost omnidirectional. So, what is near vertical incident skywave propagation? Um, we This was pretty easy to determine. We talked a lot about this. You get almost a vertical takeoff or a very sharp angle takeoff into the ionosphere. So it provides short distance, medium frequency, or HF propagation using high elevation angles. So that's what NVIS propagation is. So, what does the term NVIS mean as related to antennas? Well, we just kind of saw that. Oops, get this back in here. Near vertical incidence skywave, NVIS D. At what height above ground is an NVIS antenna typically installed? Very simple. If you're getting near vertical, you don't want it up high if you want close in communications. So typically that antenna is going to be installed between 1/10 and 1/4 wavelength above ground of the particular frequency that you're operating on. Which of the following is an advantage of an NVIS antenna? Remember, low radiation angle is not one of the things for an NVIS antenna. It actually gives you a very high vertical angle of radiation for working stations within a radius of a few hundred kilometers. What happens to the feed point impedance of a ground plane antenna when its radials are changed from horizontal to sloping downward? Remember what we said, we want to make sure that you get a proper impedance match. So what actually happens is that it increases slightly, and it's different with a dipole bringing the ends down to an inverted V. Um, the dipole, a flat dipole, has a higher impedance than an inverted V at the feed point. When you're working with a vertical antenna that has radials on it, by slightly bending them down, they the straight out, they have a rather low impedance. But if you lower them down, it'll increase the impedance a little bit closer to 50 ohms. So, what is the approximate length for a quarter wave vertical antenna cut for 28.5 megahertz? And if you remember back from your CB days, you had that 8-foot whip. So, approximately 8 feet is the length for a quarter wave vertical antenna for 10 meters. Where should the radial wires of a ground mounted vertical antenna system be placed? Okay, they can be placed either on the surface or buried, preferably a few inches below the ground. Which HF antenna would be the best to use for minimizing interference? You really want to, if you're looking to minimize interference in a particular direction, much like I have with my 2 meter 13 element beam, I want a directional antenna. So, which statement about a 3 element single band Yagi antenna is true? Think about that 3 element single band Yagi antenna. Um, let's look at some of the answers here. The reflector, normally the shortest. No, the reflector is typically the longest. The driven element is the longest. No, C is not the answer. It is not the longest. And D is not a correct answer either. However, the only correct answer in this selection is the director is normally the shortest parasitic element by about 5%. The reflector is 5% longer than the driven element. What is the approximate length of the driven element of a Yagi antenna? The approximate length of the driven element of a Yagi antenna. Typically, you want about a half wave. So always consider that those Yagi antennas, those beam antennas, are going to have a driven element at about a half wavelength. So which of these statements about a 3 element single band Yagi antenna is true? Uh, right off the bat, as you're looking down the list there, we automatically know that the reflector is normally the longest. So looking at the other three choices, none of those are correct. A is your correct answer here. How does increasing boom length and adding directors affect a Yagi antenna? Kind of be a little careful here. The boom length affects a certain aspect, whereas the size or the diameter of the elements themselves affect a different aspect. If you remember, the boom length actually affects the gain. So lengthening it will give you an increase in gain. Bigger diameter tubes will give you greater bandwidth on the frequency band that you're operating on. What is meant by the main lobe of a directive antenna? The main lobe. Okay, this happens to be, when you look at these answers here, um, the first three are really, they suck. D is your correct answer. The direction of maximum radiated field strength from the antenna. That is the main lobe of a directed antenna or a beam antenna. So, what does the front to back ratio mean in reference to a beam antenna? Okay, the front to back ratio. All right, there is a ratio of null versus the power that's going out on the main radiator being directed by the director. So the power radiation, if you look at C, the power radiated in the major radiation lobe compared to the power radiated in the exactly the opposite direction. That is your front to back ratio. Which of the following is a beam antenna design variable that could be adjusted to optimize forward gain, front to back ratio, or SWR bandwidth? Think about this real quick. just take a moment, okay? Because what they're talking about here in this question is that they're giving you kind of three things to consider. Very easy to answer this question. If you're optimizing the forward gain, front to back ratio, or SWR bandwidth, those are three things that they're trying to accomplish. And all these, when you look at these answers, all these choices are correct. So there you go. A good way to remember that one in particular: the physical length of the boom, the number of elements, and the spacing of each element along the boom. Which of the following would increase the bandwidth of a Yagi antenna? We talked about this before. Larger diameter elements will give you greater bandwidth. Instead of being able to operate only on 20 or 30 kilohertz, you can increase that bandwidth to 50 kilohertz with a larger diameter element. And what is the purpose of a gamma match used with Yagi antennas? Again, it's a little tiny stub. Remember that is right next to the driven element. Electrically, it is a short, but to RF, the electromagnetic spectrum, it is a matching network to give you the best possible match as far as feed point impedance. So the match to match the relatively low feed point impedance to 50 ohms is the purpose of the gamma match. Which of the following is an advantage of using a gamma match for impedance matching of a Yagi antenna to 50 ohm coax feed line? So there is an advantage here to consider, and the main advantage and the only advantage, as far as this is the choices here is concerned, is it does not require that the elements be insulated from the boom. Getting a little bit of dry mouth here. We're almost done, folks. What is the advantage of vertical stacking of horizontally polarized Yagi antennas? Vertical stacking. Um, it doesn't mention anything here about gain, but what it really does is it narrows the main lobe in elevation. D is your answer here. It narrows that main lobe by concentrating more signal in a direction that you have the antennas pointed to. How does the gain of two element, or how does the gain of two three element horizontally polarized Yagi antennas spaced vertically half wavelength apart typically compared to the gain of a single three element Yagi? Okay. Um, if they're spaced vertically a half wavelength apart, how does the gain of two three element horizontally antennas um, compare to the gain of a three element Yagi? And it's actually about 3 dB higher. Remember that picture of the two antennas. What is the primary purpose of antenna traps? And the primary purpose is really to permit multiband operation. Which of the following is a disadvantage of multiband antennas? There is a disadvantage. And if you remember correctly, you could be causing harmonic uh, uh, signals to be broadcast out on frequencies that you don't intend to broadcast on. So they have very poor harmonic rejection. Multi-band antennas. Which is one of the disadvantages of a directly fed random wire HF antenna? A disadvantage of a directly fed random wire HF antenna. Okay. You don't want to directly feed that because really you may experience RF burns when touching metal objects in your station. It has that propensity to reflect uh, RF feedback basically into the shack. So that's a disadvantage. What type of device is often used to match transmitter output to an impedance not equal to 50 ohms? Looking there, where did we talk about a balanced modulator or SWR bridge or a Q multiplier? Uh, the simple answer to this is an antenna coupler or antenna tuner. It helps to make your transmitter happy by giving it a 50 ohm load to look at. What is meant by the terms dBi and dBd when referring to antenna gain? Remember what that dBi refers to. That I refers to a particular antenna, and just off the top of your head, it's going to be an isotropic antenna, and the D is going to refer to a dipole antenna. Closing in on the end of it here, folks. How does antenna gain stated in dBi compared to gain stated in dBd for the same antenna? Again, that dipole, um, uh, be careful with this one because A is not the correct answer. But a dipole antenna has approximately a 2.15 dB higher gain over an isotropic antenna. Approximately how long is each side of the driven element of a quad antenna? Well, you think about quad, you think about four, and it's very easy to say it's a quarter wavelength because the whole thing is a full wavelength, and each side is a quarter wavelength times four makes up a whole wavelength antenna. What about the forward gain of a quad antenna compared to the forward gain of a three element Yagi antenna? Not much difference. They are about the same. What configuration of the loops of a two element quad antenna must be used for the antenna to operate as a beam antenna, assuming one of the elements is used as a reflector? Configuration of the loops of a two element quad antenna. Um, you should have a reflector on your antenna. It's not good practice to use the driven element as the back end with a director. You should always have a reflector. It makes it a little bit more efficient that way. But the configuration being the reflector element must be approximately 5% longer than the driven element. Approximately how long is each side of a reflector element of a quad antenna? How long is each side of a reflector element of a quad antenna? Well, we know that we're talking about a reflector element. Reflector is a little bit longer than the driven element. So it's going to be, and since it's a quad antenna, you're going to have four sides. So again, slightly more than a quarter wave length. What happens when the feed point of a quad antenna of any shape is moved from the midpoint of the top or bottom to the midpoint of either side? Okay, what happens when the feed point of a quad of any shape is moved from the midpoint of the top or bottom to the midpoint of either side? The polarization, we're talking about the polarization here. If you move it from the horizontal, your polarization is going to be horizontal. If you move it to the vertical, you're going to be having a vertical polarization. So the polarization of the radiated signal changes from horizontal to vertical. Approximately how long is each leg of a symmetrical delta loop antenna? Again, you're talking about a delta loop being a triangle, and so you have three sides. So they're approximately one-third wavelength long. Each side is. How does the gain of a two-element delta loop beam compared to the gain of a two-element quad antenna? Again, this is one of those questions where the two antennas are really about the same. Which of the following describes a log periodic antenna? Remember, that's a big monstrosity. And when you look at this big long answer at the very top of the choices here, A, the length and spacing of the elements increases logarithmically from one end of the boom to the other. Which of the following is an advantage of a log periodic antenna? The easy answer to this is wide bandwidth. It covers a wide spectrum of frequencies, and the government's allowed to do that. That's why you find it in the military or the FAA or some other government installation, they have a log periodic antenna. They want a wide bandwidth, but it has certain disadvantages too, like low gain. Which of the following describes a beverage antenna? Think about sitting back into your easy chair and you're drinking a nice beverage and you're just listening to your HF rig and pulling in the signals while sipping that lemonade. So you get a very long and low directional receiving antenna. That's what a beverage antenna is. Which of the following is an application for a beverage antenna? It actually is capable of directional receiving for low HF bands. Yeah, it is directional. You stretch that thing out, and let's say you have it stretched out north to south. Your best receiving is going to be east to west. So that's your best configuration anyway, if you're not interested in receiving anything from the north and south. But you can always put up two of them and switch back and forth. Why is a beverage antenna not used for transmitting? Well, that's a pretty easy one. It has high losses for one thing compared to other types of antennas. Which of the following most limits the effectiveness of an HF mobile transceiver operating in the 75-meter band? Okay. Following, which of the following most limits the effectiveness of the HF mobile transceiver? Okay. Remember, I told you before, you can have one of the best rigs on the market, but if you have an antenna system that sucks, it isn't going to help you one bit. So, actually, the effectiveness of your HF mobile transceiver is limited by the effectiveness of the antenna system. What is one disadvantage of using a shortened mobile antenna as opposed to a full sized antenna? Wow. The disadvantage. We're talking about the disadvantage. Um, Sorry about the interruption there, folks. Stupid phone calls. I thought I had that thing turned down. At any rate, the operating bandwidth may be very limited. That's one thing you need to really take in consideration is, how much bandwidth are you going to want to run if you're operating mobile? So there is a limitation on bandwidth as far as mobile antennas is concerned. What is the purpose of a capacitance hat on a mobile antenna? Well, the capacitance hat not only works on mobile antennas, but on base antennas as well. But what it actually does is it electrically lengthens a physically short antenna. And what is the purpose of a corona ball on an HF mobile antenna? It actually reduces the um, propensity of high voltage discharge from the tip of the antenna. So, which of the following must be connected to an antenna analyzer when it is being used for SWR measurements? Very simple answer. You want to know. I mean, you need to look at that antenna and that feed line both. So those need to be connected up. What is the use for an antenna analyzer other than measuring the SWR of an antenna system? Okay, it can help you do a lot of things. Predominantly, though, it helps you to determine the impedance of an unknown or unmarked coaxial cable. What problem can occur when making measurements on an antenna system with an antenna analyzer? Oh boy. Any rate, sorry about that. Uh, One of the problems that can occur, remember that little story of all of a sudden the SWR and all kinds of indicators are going nuts on your antenna analyzer is just from strong signals from nearby transmitters that can affect the accuracy of your measurements. So you got to be careful about that. Which of the following instruments may be used to monitor relatively to monitor relative RF output when making antenna and transmitter adjustments. Okay, which instrument RF output when making antenna and transmitter adjustments? Actually, it just takes a small field strength meter. That's all it takes. All right, which of the following can be determined with a field strength meter? Well, we pretty much just covered that. You can look at the field strength as well as the radiation pattern of an antenna. You can walk around that antenna and determine what the radiation pattern of that antenna is. So, with that, we have actually concluded the HF antenna portion of this course, and thank you for all that may be watching. You can subscribe to my channel. I'm looking for something here. Um, how many people would like to have that set up? That's actually a picture at W1AW up in Newington, Connecticut, of a lot of vintage radio equipment. I took that picture when I was up there visiting one time. They have a lot of stuff up there, and it is quite interesting. Um, how's this for an operating station? If you're a Star Trek fan, there you go. You got one of those. Any rate, I'm going to wrap this up, and the next topics that we cover will cover electrical safety, and what else did we have here? Electrical safety, coax cable. We're going to talk about coaxial cable in the next topic. I'm going to do that one on Thursday evening. And if you want to, if you're viewing this, you just happen across it, and you want to join me online live, just go ahead and drop me an email, Wayne at n3lms.net. And I'm going to stop sharing here. Wayne, again, that email address is Wayne at November 3 Lima Mike Sierra n3lms.net is my email address. Thanks for watching. Hope you're getting something out of this, and I hope to hear you soon on the HF bands with your new general ticket.